All right, so I'm going to introduce the first speaker. She's Emily Crowe. She's currently a postdoctoral researcher at the Vrije Universiteit Amsterdam with Ellie Brenner and Jeroen Smeets, where she studies sensory motor control. So welcome, Emily, and the stage is yours.
Thank you. Yeah. Can we see this okay? Perfect. So thank you. And today what I'm going to do is characterize a hand stabilization mechanism to explain the hand's response to abrupt background motion. So if I give you the task of intercepting this green ball as it moves across the screen, and then suddenly I move the background abruptly, what your hand will do is it will follow the direction of that abrupt background motion. And this is called the manual following response, and it's a very robust and well-documented effect. So basically, if the background moves leftward, my hand will follow that background leftward. And if the background moves rightward, my hand will follow that background rightward. So this has led to people asking, well, what causes this manual following response and why do we do it? And the most compelling explanation so far is that it is a compensatory response to inferred self-motion. So the idea that is, if the background moved leftward, I infer that I myself have moved rightward, and therefore I need to correct accordingly and compensate by moving my hand leftward in the direction of that background motion. And it's proposed that we use the instantaneous optic flow to estimate how much the magnitude to which I've moved leftward or rightward. There are, however, some experimental characteristics that do not support this suggestion. So first of all, the finding that it's primarily based on background motion close to the target. So this suggests that there is a bias to which motion drives the largest manual following response, and therefore it doesn't appear to be reliant upon estimating self-motion from the whole optic flow. And then second, this manual following response isn't present after illusory self-motion is induced by vestibular stimulation. So this doesn't really make sense, because if it is a response to inferred self-motion, it shouldn't matter how that self-motion is induced. So what we want to do here is propose a new hypothesis called the Hand Stabilization Hypothesis. And according to this idea, people do not actually analyze the instantaneous optic flow to estimate their self-motion, but we assume that the endpoint of our action is stable. Any abrupt motion that appears near the desired endpoint of my action is therefore attributed to that position having moved relative to myself. So during my ongoing movement, I follow any motion within that region to stabilize that movement. And what I'm going to do here is present 6 experiments that we believe provide support for this hypothesis. So the first experiments I will talk about were completed by participants stood in front of a very large screen, and they perform an interceptive action using the index finger of their dominant hand. And they were free to move however felt most comfortable. And we basically track the position of the finger throughout the entire trial. This is what the experiment task looked like, and this did vary slightly across the experiments I will present. But basically, to start a given trial, participants have to bring their finger to the black starting circle on the top left panel. After a random period of time, a target item will appear, which is the black circle, and that will start rolling rightward across the screen. And participants are instructed that they need to intercept that black target when it enters the grey circle, which is what we call the interception zone. At a fixed point during the target's motion, the background will move abruptly. This will last for 100 milliseconds and then stop. So it's a very abrupt motion. And this can occur either leftward or rightward, so is always horizontal. The target then continues moving, and the trial will end when a participant hits the screen such that they have performed their interception. For all the experiments I'm going to present, I will also use the same data analysis. So what we first do is, for each participant, we take the average lateral position of the finger from the time of the abrupt background motion. So for each participant, this gives us an average rightward response and an average leftward response, which you can see plotted here for individuals, and then the thicker lines show the average across all participants. We then convert this into a velocity, and the final step is we use this to quantify what we call a response. So what I do here is I do the average rightward velocity, sorry, minus the average leftward velocity. And this shows us whether there was a difference in behavior when the background moved leftward compared with when it moved rightward, which we define as a response to the background motion. So importantly here, if there is this positive response, then it shows the classic manual following response where the hand has indeed followed the direction of the background motion. And this is the analysis that I will present throughout the next experiments. So in experiment 1, we were interested in whether we're less likely to respond to abrupt background motion if the background is unstable. So an assumption of the manual following response is that because we typically assume the background to be stable, any background motion, any retinal motion of the background is more likely to reflect self motion than background motion. So we asked the question of what would happen if we constantly changed the background such that it wasn't a very reliable source of visual information from which to infer self motion. So we used 3 conditions. In a high stability condition, there was only the abrupt background motion on 20% of trials, such that overall you were viewing a very stable background. In a medium stability condition, there was always abrupt background motion, either leftward or rightward. And in the low stability condition, we used asynchronous limited lifetime dots, such that they looked a bit like this with flickering. So the background was constantly changing and then underwent the abrupt background motion, such that it isn't a very reliable background. And these are the results. So for each figure, I will plot the average response of participants in the main figure that you can see here. And in the insert on the top left, I present the individual initial responses to the perturbations. And what we define as the initial response is the average magnitude of the response between 150 and 200 milliseconds. So the gray bar that you can see on the x-axis. What I want to draw your attention to here is even in that low stability condition, so in the purple curve where the background was constantly changing, we still clearly display a manual following response. So this shows that any abrupt background motion is sufficient to drive this response, and it doesn't depend on us inferring how stable the background might be prior to the onset of our action. Instead, we just assume the endpoint is stable such that any abrupt background motion leads to the manual following response. In the second experiment, we wanted to ask whether abrupt background motion of any structures is sufficient to elicit the manual following response, or do all structures need to move? So specifically, we were interested in what if we only move 1/3 of these background dots and the rest of them remain static. So it looks something like this. We were interested in whether we would still get a response in the direction of background motion. And these are our results. You will also see in the legend something about color, but I'm not going to talk about that in this talk. And instead, I just want to draw your attention to the fact that in both conditions, clearly there is a manual following response. So even when the majority of background structures are static, any abrupt background motion requires us to stabilize that ongoing movement. In the third experiment, we really wanted to test just how little abrupt motion was needed to drive the manual following response. So here we had a similar idea, and only 3 out of 600 dots, so not accurately represented here, moved. So a very, very small proportion of the dots actually underwent motion. And this was either at the location of the interception zone or at the location of the target. So it looks something like this, where the majority of your background is completely stable, but 3 dots did shift leftward or rightward on any given trial. And these are the results. So again, the important take-home message here is that in both conditions, so whether the 3 dots that moved were at the location of the target or the 3 dots that moved were at the location of the interception zone, we still get clear evidence for a manual following response. So taken together, these last 2 experiments really showed that only moving dots are considered and any motion seems to drive this response, and the static surrounding background doesn't seem to be playing a role. After this, we wanted to look at trying to refine the spatial constraints of the manual following response, of our hand stabilization hypothesis, sorry. So the next question we asked was, does only motion that occurs very close to the target's path contribute to the hand's response? So what we did here was we basically split the screen in half, although the horizontal line wasn't there. And the 2 halves of the screens moved in opposite directions, like this. And we were interested in what would happen in this condition, whether participants would respond at all and whether they would follow the motion presented in the top half or the bottom half of the screen. So the first thing to note here is the golden curve, and this is our control condition basically. So here, both the top and the bottom halves of the screens moved in the same direction, and you can see that standard manual following response. The turquoise curves shows the response of participants when the two backgrounds moved in opposite directions. And this looks very different. So although there is this tendency to respond in the direction of the background motion presented in the top half of the screen, where the interception zone and the target were presented, the bottom half of the screen is clearly not irrelevant because this manual following response looks very different to the standard golden curve. For the last two experiments, we used a different setup. So here we were interested in the role of depth information. So we had two screens and background dots were presented on both screens, and the target and interception zone were always presented on one of these two screens. Experiment 5 assessed the question of whether the magnitude of the manual following response depends on where the target and background were presented relative to each other in depth. So if we take our setup, we say we have the near screen and the far screen, and in this experiment, only background dots on one of those screens would move. The target on some trials was presented on the same screen as where the background motion occurred, and at some trials was presented on the opposite screen to where the background motion occurred, such that we have a 2x2 design like this. We were interested in whether these kind of manipulations changed the magnitude of the manual following response. And what we can see here is it clearly does. So the main result that I want to draw your attention to here is the two thick curves that show the largest magnitude of the manual following response. And this occurs when the target is presented on the same screen as where the background motion occurs. And what this suggests is that depth information is important, and the relative location of the target to the background matters in terms of leading to a larger manual following response when they're in the same plane. For the final experiment, we used the same setup. And this time, there was always background motion on both screens. In one condition, the background motion moved in the same direction on both screens. And in another condition, they moved in opposite directions. And in line with the previous experiment, we were interested in what direction the hand moves in here. The first thing to draw your attention to is the turquoise and golden curves. So these are our baselines here, where both backgrounds moved in the same direction, and we can see the standard manual following response. The red curve shows the response when the two backgrounds moved in opposite directions and the target was presented on the near screen. And what you see is that in line with what we would expect from experiment 5, the hand follows the background motion on which the target is presented. The purple curve, however, is somewhat more difficult to interpret because it seems like the background, we first follow the screen on which the target is not presented, and then there's this delayed latency to follow the background on the motion of the screen where the target is presented, which is a somewhat more confusing result. But overall, to conclude, we'd like to introduce the hand stabilization hypothesis to explain the manual following response. We think that the manual following response does not rely on an analysis of the global optic flow to directly estimate self-motion, but instead that we assume the endpoint of my action is stable, such that any abrupt motion near where I am aiming is attributed to that position having moved relative to myself and requires me to perform a manual following response to stabilize my ongoing movement. Thank you for listening. I'm pleased to ask any questions.
Thank you very much, Emily, for the presentation. That was really, really interesting. Unfortunately, we don't have much time for questions. If there is one quick question from someone in the audience, we can do it, but otherwise, I'm afraid we